velocity and acceleration, because these are certainly applications of derivatives. Okay, now I need you to sort of pretend, and I know that this is a big sort of leap of the imagination, but you need to pretend for the next hour that things can only move in straight lines. They can go right and left, they can go forwards or backwards, but that's it. Okay? That's what we're going to assume. Because we don't have the ability at this stage, with the knowledge that we have, to do anything else. We don't have the ability to go in curves or diagonals or anything like that. Okay? So we're just going to start out simple. We're going to assume that we can only go in straight lines back and forth or up and down. That's sort of when we are changing our position, changing our distance, we are doing so in straight lines. Okay? All right, so velocity. Velocity is instantaneous velocity. Average velocity we've been dealing with for a very long time, right? So for example, you drive from Calgary to Edmonton, it's, I don't know, 500 kilometers. I don't know how far it is. What does it take, 3 hours to get to Edmonton? 4 hours to get to Edmonton? So it's got to be what, about, no, it's got about 300 kilometers, something like that. Okay, so if it takes you, let's say 3 hours, you're going 100 kilometers per hour. That's your average velocity, okay? That's not your instantaneous velocity, because as you know, you have to start, you have to stop, there's lights, then you got to go like through the drive-through, through Gasoline Alley, all of that sort of stuff, right? So your instantaneous velocity is changing all of the time, okay? Your instantaneous velocity, if we sort of draw, here's your distance, and here's time, okay, and so you're always moving towards your destination, okay? If you start, let's say, here's your house, and here's Edmonton or whatever, okay, so you're getting closer and closer. Your instantaneous, you're always moving in the same direction. You're always increasing your distance towards Edmonton. But, and if we were to draw your average velocity, right, your average velocity would be this. That line, or the slope of that line rather, the slope of that line would be your average velocity. Okay? Your instantaneous velocity at any given time is the limit of the average velocity over shorter and shorter periods of time, which is essentially the slope of the tangent line between two segments as the difference between the two segments, the time difference, approaches zero, right? So we're making these two get closer and closer together, and then we're taking the slope of the tangent line, which is essentially the definition of the limit. Okay, now what does that tell us? That tells us that if we call this d of t, d prime of t is the velocity function. The derivative of your change in distance, assuming your change in distance is a vector, because velocity is a vector, is your velocity. Velocity is the rate of change of your distance or your position. Okay. Now, do you guys know what I mean by vector? Does anyone want a refresher on that? A little bit? Okay. So basically the difference between a vector and a non-vector, scalar, thank you, is that a vector has direction. So for example, if I move to the right at a speed of, and basically the scalar, thank you for helping me out with that, of speed. Let's say I move to the right at a speed of 1 meter per second, okay? And then I move to the left at a speed of 1 meter per second. My speed is the same in either direction because speed does not have direction. I'm just looking at the magnitude of how quickly I'm moving. Velocity, on the other hand, implies direction. So if I move to the right at a speed of 1 meter per second, the velocity is 1. If I move to the left at a speed of 1 meter per second, the velocity is -1 because it implies direction. It implies that I'm moving left. Okay? If I move up, that implies positive. If I move down, it implies negative. Does that make sense? The magnitude of velocity, or the absolute value of velocity, is your speed. Okay, so if my velocity is -5, my speed is 5. It just means I'm moving in the left direction or in the down direction. Does that make sense? Okay. All right. And so basically, like if my distance is sloping down this way, my velocity, the slope would be negative, right? I don't actually have negative speed, but my velocity is negative because I'm going towards home, right? I'm going in the negative direction. I'm not going towards my destination. Does that make sense? Okay. Now, the rate of change, I mean, that's not something new. The rate of change of distance compared to time is speed. Does that make sense? Kilometers per hour. That's the rate of change of distance compared to time. Okay? So what we're basically saying here is the instantaneous velocity function is the derivative of your position function, of where you are at any given moment in time. Okay, it's the rate of change of your position, of your distance compared to time. Okay? Now, for example, a climber is 366 meters up a route when she drops her sunglasses. The height of the glasses after t seconds is given by the function h of t equals 3.66 minus 4.9 t squared. Okay? A, find the velocity of the sunglasses after 3 seconds and after 5 seconds. Well, we can figure out a function that represents velocity because the velocity will be the derivative of the height function. Okay, the height is sort of the position of the sunglasses. Okay? It's the rate of change of the height. And so that is going to be, well, the 366, the derivative of that is 0. So it's negative 4.9 times 2t. And that is negative 9.8 t. Okay, so for part A, if I want to know what's the velocity after 3 seconds, v of 3 is negative 9.8 times 3, which is, I believe, negative 29.4, I think, because 30 times, or 10 times 3 is 30. Yeah, okay. And v of 5 is negative 9.8 times 5, which is negative 29, I think. There we go. Okay. Is that right? I think. I think it's right. Okay. Oh, thank you. Right. Not I knew it was I knew that there was not going to be a decimal. Okay. 49. Okay. Thank you. That's better. Okay. Right. Okay. So why would the velocity in this case be negative? Yeah, she's dropping them like off a mountain. Let's say she's dropping them off a cliff, these sunglasses, and they're falling down, right? So because they're falling downwards, the velocity is negative. The speed of these things, though, if we were to talk about the speed, we would say that the speed of the sunglasses after 3 seconds is 29.4 meters per second, right? And the speed after 5 seconds is 49 meters per second, okay? But again, velocity implies direction. Okay, so that's part A. For part B, with what velocity will the glasses hit the ground? With what velocity will the glasses hit the ground? Well, when the glasses hit the ground, what's the height of the glasses? 0. So to answer this question, with what velocity do the glasses hit the ground, we need to know at what time is the height 0. And once we know that time, we can plug that time in to the velocity function. Okay, so we need to know at what time is h of t equal to 0. We need to know that first. Okay, so we're going to solve that first. Now, h of t was 366 minus 4.9 t squared. Okay, so if I put a 0 in here, and solve for t, I'm going to get 4.9 t squared equals 366. Okay, so I can divide both sides by 4.9. So t squared equals 366 over 4.9. And then I can take the square root of both sides. And, you know, if this was just an equation, it would be positive or negative, plus or minus. But because this is time, time has to be positive. So t is going to be the square root of 366 over 4.9. Okay, so that's the time that the glasses hit the ground. Once we know that time, we can plug that time into the velocity function, right? So now what we want to know is what is v of the square root of 366 over 4.9. And that is negative 9.8 times the square root of 366 over 4.9. And that, you got to get out a calculator. I don't know. 85, what is it?
The final answer ends up being negative 84 meters per second.
Negative 84?
That's what I got.
Okay. Let's see. I trust you. It's negative 9.8 times the square root of 366 divided by 4.9. Negative 84.7, so negative 85. Watch rounding. Or negative 85 meters per second. Okay, now this is why, by the way, if you were to stand at the top of a skyscraper and you drop like a quarter off a skyscraper, that could kill somebody if it hit them in the head. Because this speed is ridiculously fast, right? It picks up speed. That acceleration, if it is going to pick up approximately 10 meters every single second, by the time it hits the ground, it is going to be going at a very, very, very quick speed, right? And so you don't want to do that. Yeah.
But doesn't it reach terminal velocity?
Does it reach?
It doesn't kill them. And actually, Mythbusters did an episode on that and it didn't kill anyone. They like barely hurt.
Okay, fine. But okay, listen. I'm not giving you permission to start standing at the top of skyscrapers and throwing debris off the top of skyscrapers. Please don't do that. What's that? No, you can't do that anymore. I do not condone that behavior.
I guess not when you're not watching.
Yeah. Well, okay. Here's another one. That's why if you jump out of a plane and your parachute doesn't what's it called? Expand? Open, thank you. Yeah, you're gonna die pretty quickly.
The fall that kills you is the stop.
Right. It's not the fall that kills you, it's the stop. That's right. Okay.
The fact that your evil bones are too fragile.
All right, here's another one. So the position of a particle is moving on a line is given by the equation S of t equals t cubed minus 15t squared plus 63t, where time is greater than 0. So this is kind of like, I don't know, you can imagine a video game where something's just moving back and forth on a line or something like that. Okay, sorry? Yeah, I don't know. It's just moving back and forth. That's all it's doing. It's moving on a line, back and forth and back and forth. It's a little particle, okay? Where displacement is measured in meters and time is in seconds, okay? So A, what is the velocity of the particle after 2 seconds and after 5 seconds? Okay, so this is the displacement, and this is time. Okay. Now the velocity is going to be the rate of change of the displacement or of the position, right? So v of t is going to be s prime of t. It's the rate of change of the displacement or the position of this particle. This is part A. So this is, what is this? 2t squared minus 30t plus 3t squared, thank you. I'm just testing you, that's all. 3t squared minus 30t plus 63. Okay, so if we want to know what's the velocity after 2 seconds, v of 2 is going to be 3 times 2 squared minus 30 times 2 plus 63. And that is, I don't know, 3 times 4, 12, minus 60 plus 63, and that's 15, I believe. And then v of 5, I'll do it over here, is 3 times 5 squared minus 30 times 5 plus 63. And that is 3 times 25, 75, minus 150 plus 63 is negative 75 plus 63 is negative 12, I believe. Okay. All right. So, by the way, what happens at some point between 2 and 5 seconds? Yeah, it went the other way. It changes directions, right? Okay. So actually, that's going to come into play for part B. Part B, when is the particle at rest? Okay, so if the particle's at rest, what is its velocity? 0, yeah. So to figure out part B, we need to solve when is the derivative equal to 0? When is the velocity equal to 0? Okay, we need to set this guy equal to 0. So we're going to go 0 equals 3t squared minus 30t plus 63, and then this can factor. Plus 21. And that's minus 7 and minus 3. Okay, so that's when time is 3 and when time is 7. Okay, so at 3 seconds and at 7 seconds. For those 2 instants, this particle is at rest. Okay, C. When is the particle moving in a positive direction? Well, to figure out when it's moving in a positive direction, it's going to be moving in a positive direction when the change in displacement compared to time is positive, when the velocity is positive. Okay, so to do that, we want to know when is v of t greater than 0. Okay, when v of t is greater than 0, you could think of it this way as well in terms of the first derivative test, right? When the first derivative is positive, the function's increasing. Okay, so if we want to know when is the function increasing, that means it's moving in a positive direction. We want to know when is the first derivative greater than 0. Yep.
Why for B on the last one did we use h of t and then for this one we use h prime?
For which one?
For B, we used h prime of t, but then on the last one when we did like time before we used h of t.
For this one, we used h prime of t.
We used h t on that one and then h prime.
For B? Oh, okay. So for B, on this one, we wanted to know what the velocity was when the ball hit the ground. We didn't know when the ball hit the ground was. So we needed to solve first at what time is the height 0. And that's going to relate to the height function, not the velocity function. Does that make sense?
Yeah.
Once we found that, then we could put it into the velocity function. Okay. Okay, so back to here. When is v of t greater than 0? When the rate of change is positive, the function's going to be increasing. In this case, if the function's increasing, the particle's moving in a positive direction. Okay, so this is something that we did like in curve sketching, right? We can kind of figure this out the same way. If you think of, these are the moments when this thing changes direction. It changes direction at 3 and 7. And also, you have to remember, time is greater than 0. Okay, so we're not really going to consider anything that's below 0 in this case. These are sort of our intervals. Then we've got these factors, 0 to 3, 3 to 7. In fact, this can be inclusive, actually. If I'm being really picky, the 0 end can be inclusive because time starts at 0. And then 7 to infinity. And then the factors that we're looking at are 3, x minus 3, or no, t minus 3, my bad, because our variable here is t, and t minus 7. And then we want to know the sign of v of t, the velocity. Okay, so this is always positive. Okay, when t is between 0 and 3, t minus 3 will be negative, right? Let's say t is 1. 1 minus 3 is negative. When t is between 3 and 7, let's say it's 4, this will be positive, and then again, this will be positive. Okay? When t is between 0 and 3, t minus 7, so let's say t is 1, right? 1 minus 7 is negative, so this is negative. When t is between 3 and 7, let's say t is 4, 4 minus 7 is also negative. And then when t is greater than 7, t minus 7 is positive, right? If t is like 10, 10 minus 7 is positive. Okay, so negative times negative is positive, positive times negative is negative, and positive times positive is positive. Okay, so if we look at what's happening between 0 and 3, the function itself is increasing, or in this case, moving in a positive direction. Between 3 and 7, it's decreasing, moving in a negative direction. And then from 7 onwards, it's increasing again. So if we want to know when is this particle moving in a positive direction, I think that's the way that this question is phrased. Yes. We would say the particle is moving in a positive direction from 0 to 3, union, 7 to infinity. Okay. Do you guys know why this end is inclusive? The 0? Yeah, exactly, right? Because it starts at 0. The sort of experiment or whatever this is starts at 0. Yeah, and it's defined, exactly, yeah. As opposed to like negative infinity, which is not a defined value. Okay? So actually, if you can imagine what's happening here, what's happening is from 0 to 3, this thing moves in a positive direction. And then at 3 seconds, it's turning around. And then at 7 seconds, it's turning around again, and then it's moving infinitely that way. That's basically the path of this thing, right? This is 0. This is 3. This is 7. That's what's going on. Does that make sense? Okay. Now the last question is this. Find the total distance traveled by the particle in the first 7 seconds. Okay, now you may think that to find the total distance, you just have to find s of 7, right? Where is the particle after 7 seconds? But the problem is that s of 7 is basically where is the position of the particle compared to the origin at 7 seconds. And compared to the origin, the position is right here. Not that far. Yeah, distance is scalar, exactly. So the total distance is actually this whole chunk plus however far it went in the opposite direction. Yes. So the total distance, we need to sort of divide that into 2 chunks. How far did it go from 0 to 3 seconds? Because that's how far it's moving in the positive direction. And then how far did it go when it went from 3 to 7 seconds, and that's when it's moving in the negative direction. Okay, so for part D, total distance is not the same as position. Right? So again, if this is where it starts at 0, and then here's at 3, then it goes backwards and here's at 7, we need to basically add this chunk and this chunk. Okay? Now this, where it is here, is s of 0. Where it is here is s of 3, and where it is here is s of 7. Whoops, why did I put that in brackets? That's going to be its position. Okay, now to figure out exactly how far it went, we're looking at the total distance between those 2 points is the difference in their positions. Does that make sense? Like if I start at 2 and I end at 10, then the distance that I've traveled is 8. Does that make sense? Okay, so if I want to know the distance between here and here, I would go s of 3 minus s of 0. Okay, if I want to know what's the distance between here and here, okay, now remember, position is a vector, distance is a scalar. So let's say I switch that. Let's say I start at 2 and I end up at 10. Okay, now we kind of always know, all right, well, you went 8. No, wait. Let's say I start at 10 and I end up at 2. Now I'm like going backwards, right? So if you think about it, that's like negative 8. Does that make sense? It's like you're going backwards, so you're going a distance of negative 8. That doesn't really make sense. So how do we get around that? We take the absolute value of the difference. And then it always works out. Okay? So total distance is going to be the absolute value, and I just generally take the absolute value of the difference of all the chunks, even the positive ones, because then I don't even have to think about it, right? Even though I know that this chunk's going to be a positive distance, I just take the absolute value anyway, because the absolute value of a positive number is a positive number anyway, of s of 3 minus s of 0 plus the absolute value of s of 7 minus s of 3. Okay, now this will be positive and this will be negative on the inside, but when I take the absolute value, that'll give me the distance. Now what I need to figure out is what are all of those positions, right? So s of 0 is, what was the actual function? S of t is t cubed minus 15t squared. And then what was it? Plus 63t? Was that it? Yeah. Plus 63t. Well, s of 0 is going to be 0, so that's pretty straightforward. Okay, because there's a t term in every single term, or there's a t in every single term. S of 3 is 3 cubed minus 15 times 3 squared plus 63 times 3. I don't know what that is. 81. And s of 7 is 7 cubed minus 15 times 7 squared plus 63 times 7. And that is what? 49. Okay, so the total distance is going to be the absolute value of 81 minus 0 plus 49 minus 81. Okay, and that is 81 plus 32. Okay, and the absolute values basically just make sure that it doesn't matter what direction you're going in. You're always looking at just distance as opposed to direction. Okay, and that's, I believe, 113. And the units that we're looking at here are meters. Okay, so I mean, these applications, like, you don't ever really have these particles moving on a line back and forth. But if you can understand what's going on here, you really will have a good sense of how these sort of the position vector and the velocity vector work together with one another, okay? So yeah, if you practice some of these examples, it gives you a really good understanding of the whole situation. Okay, even though in real life, like, it doesn't really happen that often. Okay, all right, so last thing is acceleration. Okay, acceleration is the rate of change of velocity, how quickly something speeds up or speeds down, right? So if we're looking at, this is velocity and this is time, and your velocity is changing. Your instantaneous acceleration is essentially like the slope of the tangent of velocity, which means that it's the derivative of velocity, which also means it's the second derivative of position. Okay, so if you start with S of t, V of t equals S prime of t. The velocity function is the derivative of the position function. Acceleration is the derivative of velocity. Which means it's the second derivative of position. Okay, so let's try, we're going to do 2 examples and then we'll be done for today. Okay, the position of a particle is given by the equation S of t equals 2t cubed plus 5t squared plus 7t, t is greater than 0, where displacement is measured in meters and time in seconds. So part A, find the velocity and acceleration as functions of time, and then find the acceleration after 20 seconds. Okay, so v of t is the first derivative of the position function. Change of rate in position. So that is going to be 6t squared plus 10t plus 7. And acceleration is the derivative of velocity, which is also the second derivative of position. So we got to take the derivative of this. Okay? And the reason why, I mean, you don't have to write all of this stuff out, but I want you to have it in your notes because you may just be given the position function and then asked for the acceleration function. So you need to know it's the second derivative of position, right? So this is 12t plus 10. Okay, so that's part A. And then for part B, we want to know A of 20, which is 12 times 20 plus 10. And that is 240 plus 10, which is 250 meters per second squared. Okay? And then last but not least, okay, a boy throws a rock straight up over the edge of a cliff with an initial velocity of 16 meters per second. The distance above the ground of the rock is given by the function h of t equals 16t minus 4.9t squared. What is the rock's acceleration throughout its trip? Can I ask you guys something? Do you remember from quadratic functions in 20-1 that the coefficient in these application questions, the coefficient of the t squared term is often negative 4.9? Did that, do you kind of remember that coming up a lot? Okay, we're going to see why. Yeah, exactly. Gravity. Exactly. Okay, so here's the height function. We want the acceleration function. How do we do that? We need the second derivative, right? So we got to get the first derivative first, which is h prime of t, and that's going to be 16 rather, plus, minus. So 4.9 times 2t, which is 16 minus 9.8t. Now we were told that the initial velocity is 16. You can see why as well, right? Because if you put t equals 0 in, v of 0 is 16. Okay, and then, a of t is v prime of t, and that is negative 9.8. And guess what that is? Gravity. Yeah. Gravity. Okay, so that's why when you have all of those projectile motion questions in 20-1, the coefficient of the t squared term is always negative 4.9. Because the force that's acting upon it is always gravity, right? Okay, so we are going to stop there. What I will say about this is that we are going to revisit all of this stuff in our last unit on integration. And as I kind of mentioned and hinted at the beginning of class, we've been doing all this work on derivatives for almost the entire course. In our last unit, we're going to go completely backwards and work backwards, and that's what integration is. So if you can imagine that addition and subtraction are opposite operations, so is differentiation and integration. They're opposite processes. So we've been working from a function to its derivative. Integration is working from the derivative back to the function. So we have now been working from the position function to the acceleration function. when we revisit this, we'll have like an acceleration function and maybe some information about what's going on, and we'll have to work backwards to the position function. Okay? Give me 1 second.